like to thank the organizers of this meeting for giving me the chance of giving this talk. And also it's great to see you all, even if it's just virtually. And my talk deals with uniqueness results for CMC, space-like hypersurfaces, in the class of models known as Generalized Robertson-Walker spacetimes. We will expose a few new uniqueness results for this class of hypersurfaces, which can be seen in this paper recently published. So let me begin by talking a bit about the ambient spacetimes where we will obtain our results, which are the well-known family of generalized Robertson-Walker spacetimes. By this, we mean a product manifold of an open interval of the real line and a Riemannian manifold F, which has to be connected of dimension greater or equal than 2. And we will endow this manifold with the following Lorentzian metric. Okay, this is a work product in the sense of O'Neill, a Lorentzian one, where the working function is this F that appears here in this section. This family of spacetimes was introduced by Alias, Romero, and Sanchez to extend the classical Robertson-Walker models. So therefore, they include several well-known spacetimes, such as, of course, Lorenz-Minkowski, Einstein de Sitter, and the steady-state spacetimes, for instance. And the objects that we will study in these spacetimes will be the space-like hypersurfaces. That is an immersed codimension 1 submanifold, such that the Lorentzian metric on the spacetime restricted to the immersion is Riemannian. The importance of these space-like hypersurfaces comes from the fact that they describe, roughly speaking, the universe that we can measure at a given instant of time. And in these models, we can define some functions on our hypersurfaces, such as the height function, which is just the restriction of the projection onto the base to the hypersurface. We will denote it by tau. And also, since the time orientability of our GRW spacetimes enable us to endow any space-like hypersurface with a future pointing unitary normal vector field that we can denote by n, we can define the hyperbolic angle of at any point of the space-like hypersurface by using this formula. Also, we are dealing with constant mean curvature space-like hypersurfaces. Therefore, we will define the mean curvature of these subjects as the minus 1 over the dimension of the hypersurface times the trace of the shape operator. And this mean curvature has an interesting meaning in this case, since the sign of the mean curvature determines whether the normal observers, the integral curves of this normal vector field to the hypersurface, measure if the universe is expanding or contracting. In this case, if H is positive, we'll measure an expansion of the universe. So among all the CMC space-like hypersurfaces in these ambiances, there is of course a remarkable family, which are known as the space-like slices, which are just the fibers at different moments of time. These space-like slices are constitute a foliation of the space-time, and they are totally umbilic. We have here their shape operator, and their constant mean curvature is given by this Hubble function. And since the, the space-like slices are the rest spaces of the co-moving observers, which are the integral curves of this vector field partial T, here we see how the sign of the derivative of the working function is telling us whether these co-moving observers measure an expansion or contraction of the universe. Taking this into account, our goal is to determine when, under which conditions, we can ensure that a complete CMC space-like hypersurface is a space-like slice. In fact, we will obtain that it will be a totally geodesic space-like slice. Okay. And in order to do so, well, we will need a few tools, and those three musketeers that will help us to reach our goals will be Buckner's formula, a bound for the Ricci curvature of the space-like hypersurfaces, as well as the almighty maximum principle. Okay. So let me introduce briefly the tools that I'm going to use to reach our main result. And the first one is Salema, that states that given a complete CMC space-like hypersurface in a GRW spacetime, then the Laplacian of the square of the hyperbolic sign has this expression here. Okay, we can compute this Laplacian by means of the previously mentioned Buckner's formula, and here we obtain that this Laplacian depends on our usual suspects in these cases: the mean curvature, the hyperbolic angle, the working function and its derivatives, as well as the Ricci curvature of the fiber. So, and as I said, in order to reach this result, we need to make a few computations using this Buckner's technique. Our second important lemma is the following one, which bounds the Ricci curvature of these CMC space-like hypersurfaces, and states that given a space-like hypersurface with constant mean curvature in these spacetimes, if the warping function verifies that the second derivative of its logarithm restricted to the hypersurface, of course, is less or equal than 0, and the fiber has non-negative sectional curvature, then the Ricci curvature of our hypersurface is bounded from below. Okay, and we can see how these two lemmas make sense when combined with the third one, which, as I have previously said, is a consequence of the Moriyao maximum principle for the Laplacian. This lemma was first used by Chen and Yao to prove their classical Calabi-Bernstein theorem in the Laurent-Minkowski spacetime of arbitrary dimension. And later on, it was clarified by people like Nishikawa and Akutagawa, which helped to state it in this form. It says that given a complete Riemannian manifold with Ricci curvature bounded from below, then any C2 function which is non-negative and whose Laplacian is greater or equal than a positive constant times the square of the function, then it must identically vanish on the Riemannian manifold. And combining these three lemmas, we can prove our main result for our CMC spacelike hypersurfaces, which states that given a complete CMC spacelike hypersurface in a GRW spacetime whose fiber has non-negative sectional curvature, if the product of the mean curvature of the hypersurface with the first derivative of the warping function is non-negative and the warping function satisfies that the supremum of its second derivative of the logarithm is strictly negative, then our spacelike hypersurface has to be a totally geodesic spacelike slice. And with the help of our three previous lemmas, I can give a sketch of the proof here. Well, first, by using lemma 1, and our assumptions, we end up obtaining that the Laplacian of this square of the hyperbolic sign is bounded by this quantity. And here we're having the Laplacian of a function being greater or equal than a positive function due to our assumption of the supremum of the second derivative of the log of f times the square of this function. Okay? And also, from our second lemma, we ensure that the Ricci curvature of the hypersurface has to be bounded from below. So we are in a position to use this result from Nishikawa and conclude that the hyperbolic angle has to vanish identically on our hypersurface. Therefore, it has to be, and since it is complete, it is a spacelike slice. Moreover, due to the restriction on the product of the mean curvature and the derivative of the warping function, we obtain that it has to be totally geodesic. Okay. So this is our main result, and just a few remarks about the assumptions that we have been using. And more precisely, I will firstly talk about the assumptions that we have not used, where we have not imposed any bound on tau, on the height function. Therefore, our hypersurface can approach the future and past infinities. Okay, this assumption of lying in a slab has been commonly used to deal with the non-compact case. For instance, in an article by Galias and Montiel, they used this assumption. We are neither imposing any bound on the hyperbolic angle, so the normal field can approach the like boundary as much as we want. And we have neither imposed any compactness assumption like parabolicity, which was an idea used by Romero, Rubio, and Salamanca to deal with the non-compact case. And these are the assumptions that we haven't used. What do our assumptions mean? Well, the bound on the curvature of the fiber, asking it to be non-negative, and the bound on the second derivative of log of f, well, they imply the null convergence condition, okay, which is a well-known energy condition commonly used, which states that it can be seen as a way of saying that the gravity on average is attractive. And in fact, if we omit the assumption on log of f, then we can find counterexamples where uniqueness results, for instance, just in Minkowski spacetime. We find, well, the maximal space-like hyperplanes, which are not necessarily slices. Also, this assumption on the sign of the mean curvature compared to the
Professor, just a little remark. 1-2 more minutes, okay?
Okay. Yeah, thank you. This was I'm about to conclude.
Okay, perfect.
So yeah, this assumption can be seen as a way of saying that, well, if on the points of our CMC space-like hypersurface, the comoving observers measure that the universe is non-contracting, and the normal observers measure that the universe is non-expanding, or vice versa, then the spatial universe is actually, that is static. I mean, that we are on a space totally geodesic, space-like slice. And well, this result, particularized for the maximal case and flat fiber, can be seen as we will reobtain a previous theorem I obtained with Romero and Rubio. And just as a consequence of this parametric result, we can obtain this Calabi-Bernstein type theorem for the maximal case, which states that given a smooth function whose infimum is non-negative and the supremum of the second derivative of the log is strictly negative, then the only entire solutions to the maximal hypersurface equation in a GRW space-time, a complete Riemannian manifold with non-negative sectional curvature, are the constant functions. Okay. And well, thank you very much for your attention.